Hello everyone, welcome to Statistical Foundation for Big Data Analysis. We will continue with the introduction module, and today in this second lecture we will talk about big data analysis versus big data processing and the role of high dimensional statistics in big data analysis. Now, in last class we saw what big data is and the various facets of life, various facets of modern life where big data appears, and frankly these domains from where the big data is becoming very prevalent, that the number of those domains are expanding every day. We saw fraud detection, cyber security, meteorological situation, we saw of course this social network data, we saw various examples, we saw e-commerce platforms, we saw videos and images, the streaming platforms like Netflix, YouTube. So, all those things we discussed in last class. Now, today we are getting into more sort of structured study of big data. Now, study of big data is actually broadly it can be characterized into two different parts. One is the big data processing part, the engineering part of big data, and another is the big data analysis part, the classical statistics tools tailor made for big data, for handling big data. Those tools are the theories of classical statistics and the tools of classical statistics, how they are applied to analyze big data. That is another part. Frankly, this is the part which is the main topic of our course. So, the engineering part we will not be that much concerned with. We will talk about the statistics or the data science. In this course I will use the word statistics and data science to mean basically the same thing. Now, let us discuss little bit about the big data processing part, because last time we were talking about various facets of life where big data comes and is becoming relevant. One topic, remember, just to give an example, we discussed was meteorological data. Now, the data collected by GPS and satellite, so for data collected by satellites and drones, etc., they are prevalent in every facets of life. I mean, GPS for example uses that, which all these radio taxi companies like Ola, Uber, they use this all the time. In fact, we are also using GPS while driving, or even in India just to search some location we use GPS all the time. Now, the point is, here is one interesting fact: the satellites and drones, etc., they are continuously capturing signals in space. The amount of signals, amount of data they are constantly getting, constantly collecting almost automatically, the real time data is enormous. I mean, there is no storage space for frankly for any country or anyone to actually store all those data and process that. It is not possible. So, there are many methods to discard junk data, unimportant data, repeated data immediately, and then extract the data that is actually useful and use that. So, this whole process of cleaning and processing and storing big data, the big data processing part, is a huge part of big data science, the science of big data. This is something we will not discuss in this course, and just to warn, this is actually quite important, but this course is mostly about processed, cleaned big data and how they are analyzed. The emphasis will be the analysis part of it, and by analysis we simply mean the statistical analysis. Statistics provides the grammar of it. We will see in the subsequent lectures how statistics provides the grammar of it, how statistics gives you insight, and how what are the sort of, we will discuss the selected topics in statistics to give you a good glimpse of good understanding of how database inference is done. But before I move on to statistics part, a little bit of I just wanted to discuss briefly a bit about big data processing. So, processing of big data, first of all, one huge challenge with big data is the big data analysis, big data storing part, the storing of big data. This is a huge part of big data, because frankly storing a data, and because the volume of big data is so huge and it's getting generated literally in the real time, the challenges companies face, how much space they would allocate for storing big data, because of course since this is becoming, they are coming in real time, companies have to pre-allocate space, and how much is enough, and how much will not be wasteful. These challenges are something continuously companies face. And secondly, another huge challenge, once you have stored the data, how do you actually store it? Once you have stored the data, you have to access it, you want to analyze it. I mean, the emphasis of this course is big data analysis. So how do you, to analyze the big data, you need to access the stored data. You will not access the whole data all the time and go from starting to the end. You want to access certain parts of big data. So you have to kind of go to certain locations of that big data stored in some places. So how do you efficiently store so that can be accessed for analysis? And frankly, as the volume and complexity of the data already says, analysis cannot be done by just one team. It's almost always multiple teams will have to access and collaborate. So this collaborating for analyzing big data, like they have to be analyzed from multiple different perspective, and then finally the results have to be, and the analysis has to be collaborated to get into the final analysis. For example, when you are talking about social media, let's say YouTube, maybe one group will analyze the video part of it, one group will analyze the text part of it, let's say the comments that are coming after the YouTube video, and one team will analyze the network aspect of it, like individual profiles who are visiting which profiles are visiting which profiles, and then what is the connectivity structure. If you view the profiles, each profile as, let's say, a point, let's say, just to give you a simplistic idea, suppose each profile is a point, and if a profile visits another profile or there is some interaction, there is a line between the points. This structure, once you create this shows, for example, this node has a special role, in a sense, like this either visited every other node or is visited by some other. So take any other node, this node either has visited that node or that node has visited this node. So this node plays some important role in this whole network connectivity, and this kind of connectivity structure, visiting and interactive structure, is something which we want to study quite a lot. I mean, this is very important for analyzing social media data. So we will get into that. But multiple groups have to analyze various aspects of these big data sets, and then their results have to be combined together, so they have to collaborate. So storing of big data so that different groups can access it and they can work together is a big challenge. And generally speaking, distributed file systems like Google File System, Hadoop, they provide some sort of modern approach to do that. So in distributed file systems, what happens is that, like, files are stored in several locations, but in certain way that to the users they appear like they are stored in the single location. So multiple computers are kind of networked in such a way that different parts of the files are stored in different computers, but there is a kind of a fixed ordering, so that when the user is actually accessing this networked storage system, they to them it appears like single file. So different users can access this network distributed system at the same time, and these things appear as if they are accessing the same file, so they can separately work and eventually collaborate. Another thing is cluster computing, kind of a related philosophy, where essentially computing itself is done in a, just one second. So this is again this, I mean, we will see this notion of network will keep repeating itself in this course. So cluster computing is also something similar, where computing itself is done on, parts of computing is done on, you have to do a big computing. There are several computers, each of them does certain parts of the computing, and then they are kind of combined in a predefined way, like certain parts of computing has to be done first, then it has to be done by the other people and so on. So, they have this kind of a directed network system where this person is doing first part of the computing, sending it to the other one, this is sending it to the other, and also it need not be just in this linear fashion. There are these notions called parallel processing. So, multiple processors can do the calculations of different parts simultaneously. So, this networking and shared resourcing and parallel processing, all these plays a very big role to take the load, the heavy load that big data comes with. And finally, of course, in this case there has to be a centralized management system which makes sure that everything is being done in sync. The other aspects of big data processing that will be that's very important is functional programming. The usual object oriented programming like C++, etc., they are fine, but there is a new paradigm in programming. There is a very advanced paradigm called functional programming. That's also quite useful for big data analysis. So, languages like Scala or even Python has certain functional programming paradigms are very useful in big data analysis. So, also there are this thing called Apache Spark, which is a fast data processing on cluster, which addresses this to address process data on cluster. If you have a data cluster, how to process it very fast. This is specialized software for that, this Apache Spark. Apart from that, of course, processing various different kinds of data. We were talking about social media, so there is this video data, this stream data, we are talking about graphs, like various profiles are connected to each other by visiting and showing interest in each other's work. That sort of network structure, that is also something one has to process. So, for each of these specialized big data, specialized type of big data, different challenges appear, and one has to deal with them in a different ways for processing those kind of big data. Now, are not too much concerned about big data processing in this course, as I kept telling you repeatedly at the beginning of this talk. We will get into this next part of big data, the other part of big data analysis part, which is leading us to statistics, the main topic of this course. So, statistics is the science behind data analysis, and frankly it predates big data by centuries. Even if you are any kind of data based inference you want to do, let us say you want to discuss a simple thing, the relation between height and body weight. So, now it is kind of obvious that the taller people on an average tend to have higher body weight. Now, of course, this is on an average statement, or a statement like a general statement, taller people tend to have. There may be much taller people with much lesser body weight. I mean, a tall person can be very skinny and a short person can be obese. So, it is not sure short rule, but the point is, if your goal is to still come up with some sort of concrete statement instead of this general vague statement that taller people has higher body weight, what will you do if you want to come up with a concrete statement? Well, what you can try to do, you can try to come up with a relation like this. So, this suppose W is the weight, and so this is suppose weight, and suppose H is height. What you can try to do, you can try to come up with a function, some function f. So, this is height. What you can do, come up with a function by using some way which will predict W in terms of height. Now, of course, this function will be a mathematical form. How do you come up with such a function? The approach statistics takes, it collects some data. So, it collects let us say for 100 people, it measures height and weight, H100, W100. So, for 100 people, 100 randomly chosen people, it has registered the height versus weight. And using this data, it tries to predict this function, it tries to come up with this function. Now, one obvious way, how do you do this using this data? You kind of plot that, and suppose this is the plot for 100. Just looking at it, one can try to guess. I mean, just looking at this plot, one can guess that this line is an approximation, a decent approximation for this function. I mean, I am giving a very naive approach, but the point is, however advanced statistics you use, this nature that it is an approximation will remain. The reason for that is you will collect data, you are trying to guess based on the pattern you observe in bunch of people, you are trying to guess a pattern for all people or everything, the generalities like all people, in this case heights and weights of all people, based on the pattern you see in bunch of people. So, of course, what you observe in these in 100 people may not be completely representative. What you can try to make sure that these 100 people covers all age groups, gender groups, linguistic groups, all sorts of things. You can try to make this sample as precise as possible. I mean, like, you know, I mean, in India, opinion polls and exit polls are very popular. Suppose you are trying to predict the general election and you just collect data from one particular state. Obviously, that will not be reflective of the, like, it will still give you some insight, but it will probably not be reflective of the whole nation's mood. Similarly, if you are trying to predict height and body weight, let us say you just pick data from people who have high blood sugar, that may not be reflective. The blood sugar may have something to do with body weight, but blood sugar may influence the body weight much more in those patients than height. So, the point is what I am saying, but here is a catch, because potentially let us say you are trying to find a general formula for that will give you relation between height and body weight of all Indians. However perfect you try to do, however big data set you do, there will be still many people outside that. So, this will always be an approximation. So, this is what statistics generally tries to do. Now, for big data analysis, what happens is that due to the massive volume and massive complexity, the classical statistical tools that gives you prediction becomes very, very inefficient. Just to give you a simple reason, let us say, you know, in this course, as the prerequisite says, a little bit of linear algebra, exposure to linear algebra and probability will be useful. Just I am taking some liberty to use some linear algebra term. One method is very much prevalent in statistics is equation solving. You have to solve certain system of linear equation. Now, what happens is that if you apply simple linear equation solving method that is relevant in statistics, usual statistics for big data, simply the number of variables and the number of equations will be huge. So, simply your simple system, I mean, you can just, if you want to do this kind of a curve fitting, which nowadays even a calculator can do perhaps, will just not be possible for big data, because simply your memory will get exhausted. So, the amount of data available itself makes the traditional equation solving machines, equation solving tools simply incapable of dealing with it. Of course, I mean, this is just a simple example, this probably can be tackled with just this little aspect of it, but there, for more advanced tool you want to use, the more advanced computations will be involved, more advanced algorithms will be involved, and then more complex those algorithms are, they will struggle more with big data. So, the problem ultimately is that the data analysis, data will be presented in some mathematical form, different aspects of that mathematical form will represent different features of the data, just like here it is a 2-dimensional tuple, it's just a pair H and W, where H this data is like H and W. H represents weight and W represents H represents height and W represents weight. These are two features. Big data may simply have millions of such features. So that is the key aspect and the key issue with applying statistical analysis for big data. Now, just to discuss mathematical representation of data points, just this is actually quite good, like this we can use the same thing here. A tuple, so generally speaking, so we call a tuple of real or complex numbers a vector. The most classical format, data comes in a tuple form. So for the problem of modeling height and weight, this is let us say the height in centimeter. So let us say height in centimeter, and this is weight in pound. So traditionally a data comes in this kind of vectorial form, like it is just a tuple of things and each position indicates a particular feature. So just to give you a actual height and weight data, this is something I collected from Kaggle. This is height and weight data for real time height and weight data for 7 people. You can see that there are 7 people, and this column represents height, this column represents weight. As you can see, height weight data will actually be real, potentially real numbers. Of course, in computer there is a limitation of how much floating points you can go, how many points after decimal you can go, but potentially real, and the heights and weights can be any real number, any non-negative real numbers in theory. Another example of traditional data is a genome sequence data. This is also I got it from Kaggle. By the way, this is just a snapshot. We have only taken few data points and only 7 genes. So for the genome sequencing, this actually potentially this can give you a big data. There are millions of genes. So genome sequencing, genome data, this is also we discussed in last class, also is a very rich source of big data, and if it can be analyzed properly, it can bring revolutions to personalized medication. So this is also potential. Just to give a snapshot, the genome sequencing data will have many columns and many rows. The columns will represent various features, in this case various genes. But the point is, data may not come in this traditional vector tuple form. We just were discussing about the prevalence of this network data. Now take any social media, let us say take Facebook. So if various points, if various points, let us say for now denote, so I am just taking bunch of points, let us say these are Facebook profiles, and for now I am joining 2 profiles if one is friend to another. I am not friend, follower, I am not distinguishing them. Let us say we will join them if one is friend of the other one, 2 nodes we will join if they are either friends or one follows the other. So let us just take a imaginary friendship kind of relationship connection. So let us take this kind of thing. Now the point is, if you want to analyze Facebook data, and Facebook data analysis is becoming really important. First of all, it is becoming important for commercial purpose, because people want to see which are the profiles you go, and because profiles are not always profiles of other individuals, they can be for some companies, some commercial agencies, some nowadays even groceries shopping, specialized targeted grocery shopping also can be done using Facebook. And then depending on that, Facebook provides you personalized suggestions, and this can go to many things. Sometimes security apparatuses, like they track Facebook data to denote suspicious activity, fraudulent activity. So for this kind of thing, the network structure is extremely important to study, like whether there is a cycle structure there, whether there is one particular node where obsessive amount of connection is happening. So, if you take something like this, in this network clearly this node has a special role, every other network or every other node is connected to this. So, this kind of network connectivity structure, network structure is something that is needed to be studied in case of social media and other many network format. For example, another thing is that human metabolism network or cancer metabolism network, where one has to study gene network or gene protein network, which is extremely important for medical research. Now, just in simple term, a network data involves at least two things, nodes and links. In formal mathematical term, nodes are called vertices and edges are the links. So, these are nodes and these are links. So, if you look at this, these A, B, C, D, E, these are nodes and there are links between this. There can be various different modifications, various different improvement. For example, there can be directions in the nodes, there can be weights. For example, vertices can be weighted by some, let us say, non-negative integers, not necessarily non-negative, there can be negative also. Well, let us not talk about the negative now, let us say just those intricacies may come later. So, these things can be weighted, there can be some weights, there can be some weights on the edges also. Various modifications can be done. I mean, in many ways they represent. So, for example, in case of Facebook data, the weights potentially weights can be for each node, weights can denote the number of friends that person has or number of visits. Say, let us say we do the link structure as friendship and let us say weights to be the number of visits or number of followers that particular node has. All these things can happen. Now, one example of graph data will be if you take a big network, let us say Facebook, and for each node create a small graph where let us say you will choose all the other graphs, all the other nodes which are at most k distance from that. So, look at this graph and let us discuss this. So, we are discussing the, let us say the let us discuss the two distance friendship neighborhood of this graph. Yeah. So, let us discuss the two distance friendship neighborhood of this graph. If you look at the node A, B and C are connected to this and the node D is two distance from this. Why? D is a friend of A. Similarly, for B also it is connected to A and B, and D is at most two distance from B because it is a friend of B. So, for both A and B, the two distance neighborhood graph will be A, B, C, D. But for C, for example, A and B are friends of C, D is a friend of C and E is a friend of C. So, two distance neighborhood graph for C will be the whole graph. Similarly, for D, C is a friend of D, E is a friend of D and A and B are friends of D. So, they will also be in the two distance from D. So, for C and D it will be the whole graph, for A and B it will be just A, B, C, D, the graph restricted to A, B, C, D. And finally, for E, the only friend of E is D and the friend of E is just C. So, for E this will be the neighborhood graph for two distance neighborhood graph of E. And I mean, I do not want to get into too much details because I am just trying to give you a glimpse of it. One can do many modifications of this, one can do the weighted graph as I was saying, like then one can kind of do this weighted neighborhood graph. Various features will be just these neighborhood structures, this so called combinatorial structures as well as weights, many versions of this can come. Another kind of data that can come as matrix. Now, there are various interesting ways one can do matrix data. One important matrix data is the important source of matrix data is the two dimensional images. images comes as pixels, and for example, this is a picture of a pixeled image. This is a handwriting detection data. So, if you are written as 6, you just look at the pixel values, take certain size, some something like 256 cross 256 or 728 cross 728 grid, and at every grid point if there is a black dot take 1, if there is no black dot take 0. So, this gives you a 0 cross, this gives you a big 0 1 matrix. It does not have to be 0 or 1, you can also kind of increase it into 0 to 9 in terms of intensity. If there is nothing, it is 0. If a very mild line, that is mild dot, it is 1, slightly brighter 2, and so on, and then the most brightest will be 9. So, then you will get a integer matrix where each entries will be 0 to 9. So, that kind of pixel data comes from many image processing contexts. So, not just handwriting detection, medical image processing, ultrasound, X-ray, CT scan, etc. They come as matrices of this form. Now, here is a catch. Matrix data like this can be obviously viewed as also as a vector. Like for example, you can simply flatten out the matrix and visualize this as a vector. So, any m cross n matrix can be visualized as a vector in mn dimensional Euclidean space. Graphs, for now we are talking about the undirected unweighted graphs, but there are weighted versions of it, can be viewed as matrices. And the fact that matrices can be viewed as vectors, because graphs can be viewed as matrices, they can also be viewed as vectors. So, here is a way to visualize graph as a matrix. There are other ways also, it is called adjacency matrix. So, if suppose there are n vertices, n nodes, you take an n cross n matrix and the ijth position is 0 if I and j nodes are connected, and 0 if I and j nodes are not connected. This gives you a symmetric matrix. So, here is an example. You have taken 4 nodes, so 4 cross 4 matrix. One is, so none of the nodes are connected to itself, so zeros on diagonals. One is connected to 2, so there is 1 in the 1 2 position. One is connected to 3, so there is 1 in the 1 3 position. One is not connected to 4, so it is 0. 2 is connected to 3, so 1 here. 2 is not connected to 4, 0 here. 3 is connected to 4 here, so 1, and it is symmetric. So, graphs can be converted to matrices. So, and because matrices can be converted to vectors, so graphs also can be converted to eventually vectors. So, what happened, what this tells you, the classical vector based multivariate statistical method still remains relevant to studying these kind of structured data like graph data or matrix data. So, big data immediately leads into analysis of big data, multivariate statistics of very high dimension. So, I stop today's class here. Thank you.